Otherwise, at this point, we're going to move on to our final talk. This is going to be given by Olivia Leavitt. Apologize, I've lost my, her talk is titled Prosthetic Stimulation in the Axis Corresponding to Support Surface Perturbation Improves Postural Control in a BVL Primate.
Good afternoon, everyone. I'm Olivia Leavitt. I'm from the Cullen Lab at Johns Hopkins University, and I'm going to be presenting some preliminary data on prosthetic stimulation in a primate model with vestibular loss. The vestibular system consists of 5 organs in the inner ear that sense the angular velocity and linear acceleration of the head. Signals in the vestibular system are carried on the vestibular nerve by regular and irregular afferents to the vestibular nuclei, which contribute to visual stability, self-motion perception, and posture and balance. In the absence of vestibular signals due to vestibular loss, all of these functions are impaired. An emerging approach to treating vestibular loss is the vestibular prosthesis, which uses a head-mounted gyroscope and a microprocessor that uses a mapping function to translate the angular velocity of the head into a stimulation pulse train that can be delivered to any or all of the semicircular canals in the vestibular labyrinth. Importantly, the electrodes primarily activate irregular afferents, which also happen to be the primary contributors to posture and balance downstream. One such prosthesis is currently in clinical trials in humans at Johns Hopkins, and it's been successful in restoring patients' confidence moving through the world, but some aspects of their performance require further development. So here we're using a rhesus macaque model, which allows us to not only probe externally measurable factors like posture, as we do here, but also probe vestibular pathways in the brain and better understand how the prosthesis may be interacting differently with the brain than the native periphery. In humans, balance is often measured by applying perturbations to the support surface. When the frequency of perturbations is low, the head and center of mass remain stationary relative to the platform, while at high frequencies, the head tends to remain fixed in space. The strategy switch from what we call platform fixed to a head fixed strategy results in high gain at low frequencies, followed by a switch to low gain at high frequencies. In humans, this strategy shift occurs around 0.3 hertz. In monkeys, we expect to see a similar strategy shift, although the frequency the strategy shift occurs at may change depending on the animal's biomechanics. For this study, I delivered sine wave perturbations in the roll axis on a hexapod motion platform while the animal stood in a chamber. The monkey's motions were measured with a force plate with an IMU, as well as joint tracking using markerless pose estimation with deep lab cut. Here's an example of the traces that come out of the data once it's synchronized in post-processing. As you can see, the data is very multimodal. There are 12 analog type inputs as well as up to 20 joints being tracked. Here I'm focusing on just the head roll because it's easy to connect to postural sway. Here is the sway response in a normal animal. In a monkey with an intact vestibular system, the gain curve for postural sway mirrors that of humans, although the strategy shift here seems to be occurring at around 1 hertz rather than at 0.3 hertz as it does in humans. In the case of vestibular loss, monkey had higher gain over all of the frequencies, which means that there was more postural sway at all frequencies, which we would consider to be poorer posture and poor postural compensation. With stimulation in the posterior canal, which senses movement in the roll and pitch axes, there is a slight decrease in gain from bilateral vestibular loss in most frequencies, which indicates improved posture. This is particularly true at high frequencies. This makes sense because the posterior canal is sensing movement in the roll axis, so any movement that is sensed would help contribute to improving postural compensation. In contrast, when the horizontal canal is stimulated and the horizontal canal senses movement in the yaw axis, there was much less postural improvement overall, and particularly at low frequencies, the animal tended to sort of tip over as the perturbation reached its peaks. In summary, the vestibular prostheses are an emerging treatment for vestibular loss, but there is opportunity for improvement. Rhesus monkey postural responses resemble human postural responses, but with a higher strategy shift frequency, which is as expected. Bilateral loss does cause increased sway across platform perturbation frequencies, and vestibular stimulation appears to at least partially restore posture, particularly at low frequencies. And with that, I'd like to thank my colleagues in the Complement Lab.
Great, thank you, Olivia. That was really nice. It's amazing how, like you said, multimodal the data is. So seems like really interesting stuff. So I guess I'll ask one question that was kind of sticking out in my mind. Is the translation between how you think that the postural stability should work, as in, are the monkeys going to be doing the same thing that a human would be doing, because monkeys aren't bipedal and they have a tail?
So one of the things that was really interesting doing literature review for this work is that most human, as this image shows back here, most human work is done in the anterior posterior tilt, so pitch tilt. And because our base of support is sort of horizontal relative to our shoulders, that makes sense. I decided to change to roll because that would be the primary unstable axis in a monkey model because they're quadrupeds.
Cool. That makes a lot of sense. So we've got two questions. I believe both are, one is definitely panelist asked, so I'll ask that one first. What insights do you gain from your results that could be incorporated into the pre-existing vestibular prostheses?
In this case, I think the biggest thing to think about in terms of prosthesis development is to ensure that all of the canals are being stimulated, because early prostheses and early work primarily focused on the yaw axis because that's where a lot of the research has been done, and also it was thought that head turns would be a primary perturbation for someone with vestibular loss. But given these results about posture, it's important for maintaining posture and probably gait as well to have stimulation in all of the semicircular canals, if not also the otoliths.
Great. So Robin also has a question, so you can unmute yourself and turn on your video on.
Okay. I'm wondering if you've tried to relate that difference in the transition frequency between humans and monkeys to the height of the center of mass, and quantitatively?
I haven't yet, but I'm assuming that because it's a shorter pendulum, it would be because of the lower center of mass and the shorter limbs.
Great. And Omid has a question as well. Do you expect the performance of unilateral vestibular loss animals to be closer to normal or bilateral with vestibular prostheses? So you go ahead.
Because the prostheses are generally implanted unilaterally, I would guess that with a perfect prosthesis, a bilateral loss animal with a unilateral prosthesis would perform closer to a unilateral animal. But a unilateral animal would likely not have quite as good posture as a bilaterally native or a normal animal.
And then Richard's going to ask the next question.
So we have another question from Yvette, who asks, do you think regular afferent stimulation would be useful and or integrated with irregular afferents in the future? And while you're at it, I wanted to ask this question because my question was, could you tell us a little bit more about the hardware of how you actually conducted the stimulation and could potentially produce regular?
The irregular afferent stimulation, I believe, is due to the hardware. I'm not entirely sure. And it's also has to do with the just higher excitability of irregular afferents in contrast to regular afferents. Because regular afferents are more involved in velocity storage and visual stabilization, I think it would be helpful to also figure out a way to stimulate regular afferents at some point. But right now, the way that the vestibular prosthesis works, it's unlikely that we'd be able to do that.
Okay, John had a question. Did you check VOR gains? How long did the monkeys get to habituate to the prostheses?
So in this study, I didn't personally check VOR gains, but the monkey that I used had relatively low VOR gains relative to normal. I'm not entirely sure of the exact numbers, but VOR gains were checked.
Great. So we have time for a few more questions. If anybody has those, they can post. Yeah, I'm really interested in that regular versus irregular afferent stimulation. That's very interesting. Oh, here comes John has another question. What lesion was it? Canal plugging? Question mark.
The lesion was introduced in the process of implanting the animal, so the electrodes themselves plug the canals.
Robin says, have you tried to estimate COM with deep lab cut or IMU? Would the results be different from the head in monkeys?
I'm currently working on trying to get either an IMU or the center of mass measurements with deep lab cut. One way that I have tried with one of our more cooperative monkeys was having a vest with an IMU on the back of the monkey in addition to on the head. I would anticipate that it would be a slightly more stable signal just because the monkey does shake his head and stuff during the experiments, but I think the head is a decent analog for now, and it's just much easier to fit an IMU to the head. Okay, with that, I think there's a few more questions, but I think we'll just wrap up. So I want to thank the panelists.